integration and linear analysis class. So today we will check solutions to some exercise 6 in section 1p of our textbook we are using. My name is Sondolo Afemi, a PhD student from the Department of Mathematical Sciences in Indiana University, Indianapolis. Don't forget to subscribe and like the video and kindly share with fellow PhD students in mathematics. Alright, the first question we have define a function f on R as follows. Our f of a equals to 0 if a is irrational, and then our f of a equals to 1 over n if a is rational and n is the smallest positive integer such that a equals to m over n for some integer m. So we have to show that f is Riemann integrable and compute the integral of 0 to 1 of the function f. So I'm going to reduce this so that we have enough space to show the solution. Alright. Okay. So we know that a function is Riemann integrable. A function is Riemann integrable if we can find for any epsilon greater than 0, we can find a p such that the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon, can be arbitrarily made small. Okay, so on that note, so we can now let's check the for any partitions proof. So let P be any partition of A comma B. Okay, so if P be any partition of A comma B for any sub-interval, okay, let's say P equals to x naught is 0 equals to x naught x1, that xn equals to 1. So for any sub-interval, let's say sj common s sj minus 1 sj. So you will notice that our infimum f over every sub-interval will be equals to 0 because our a is irrational and irrational is dense in 0,1. Why? Reason is that there will always be an irrational in our sub-intervals. So no matter the sub-interval you picked, there will surely be an irrational number, and that will be the infimum of f of xj equals to 0. So then if that should be the case, lower Riemann sum of the partition regardless the length of the sub-interval or the mesh size will always be 0. Okay, so however for the upper Riemann sum now, supremum of f, then I check condition for supremum f. So case 1, if the subinterval contains a and then contain a rational, or let's first of all check that if the subinterval does not contain a rational, does not contain rational, that means that our sub f over such subinterval sj minus 1 sj will be equals to 0. But case 2, if our subinterval contain a rational, that means that our sub f over such interval is j minus 1 sj will be equals to 1 over n. Okay, so let's define the partition. So let Pn be a partition of a comma 0 that includes what? That includes rational. So for such points, our infimum will still be 0, okay? Because just our rational number is single and irrational number. We have much more irrational number in a subinterval than rational. So our sub f of sj minus sj also said will be equals to 1 over n. Then you will notice that that as n tends to infinity, our sub f sj minus 1 sj will also tends to 0. So that means that we can refine our partition. So this implies as we refine our partition, p tends to 0, then the upper Riemann sum UFP of a comma b it also tends to what? And that which also tends to 0. Okay, so if we refine our partition enough, then we have this condition. So therefore, we can say that the upper Riemann sum the upper integral a comma b is minus the lower Riemann integral, which will always be 0, be equals to the upper Riemann integral. And then if we take the partition and refine the partition enough, then we see that this tends to 0, which should be equals to u of f a comma b. So hence our f is Riemann integrable and then an integral from 0 to 1, f is equals to u of f comma a comma b 0 not comma is 0 comma 1. Condition this to 0 comma 1, 0 comma 1, 0 comma 1, 0 comma 1. So 0 comma 1 will be equals to 0. Okay, so you can also include f is Riemann integrable, since we can find a refined partition for any external greater than 0 such that the difference between the upper Riemann sum and the lower Riemann sum is less than epsilon. So that completes that proof. So let's check the next question. If you have any question, you can kindly drop it at the comment section. Question number 2. So we have suppose f is a bounded function, prove that f is Riemann integrable if and only if those conditions hold. So let's go check the forward direction. So the forward direction assume f is Riemann integrable. Then for any external greater than 0, there exists a partition P such that unnecessary. We don't need the partition. Okay, let's go ahead. There exists a partition P such that uf comma a comma b p minus n f of a comma b b is less than s normal, and then u of f a comma b is equals to n of f a comma b is equals to integral a b of f. So take note of this condition. So now we want to show n minus f of a comma b. So this is equals to what? So by definition, this is the sum over all the partition P and the lower Riemann sum minus f a comma b comma p, and that is sub p summation j equals to 1 and depend to the nth partition we defined, u of n, and then the infimum minus f s j minus 1 common xj. So if you take the infimum of a negative function by properties of infimum, that will be supremum. So you are going to have sup p summation j equals to 1 to n minus sj minus sj minus 1, then this will now be sup f, and just by the properties of supremum. So we have that. So if you also take the sup of this negative function, you are going to have minus infimum of this function. Infimum is j equals to 1 n sj minus sj minus 1 sup f sj minus 1 sj, and this is the definition for the upper Riemann sum. Okay, and that is equal to minus U F A comma B. Okay, so and since by star this is equals to minus N F A comma B, and that in our proof, because by star we say this is equals to this, so instead of this guy we can just put in this guy, then we are done. So the next thing is to prove the other direction. So assume by hypothesis that this guy is odd. So we want to prove that f is Riemann integrable. So I mean that u of f a comma b so this we can equate this using the properties or the definitions of this, or we can have it this way: minus n f a comma b is equals to n f a comma b, and you are very careful. We show that this is the same thing as minus u f a comma b. Okay, you know that from here we are able to show that that equals to this. So that means that if this is equals to this, then this also equals to this. Okay, and if that holds, then you can just cancel this negative, then we have this, and that looks so trivial, and that end our proof. So let's go to question number 3. So question number 3, we have if suppose f and g are bounded functions, we have to prove that the lower Riemann sum, the upper lower Riemann integral of f plus lower Riemann integral of g is less than or equals to the lower Riemann integral of those functions, and then the same thing for the upper Riemann sum. So we can just go by the properties of supremum and then infimum. So first, prove not by the properties of sup and then infimum. Sup f plus g over any partition is obviously less than sup f over partition p sup f over partition g. So if this holds, then you are done with upper f plus g over a comma b will be less than u f a comma b plus u g, so this should be g. Oh, so p g a comma b. So you can also prove this further by showing the upper Riemann and the lower Riemann sum and the upper Riemann sum and make it more explicit, but this is just the key. And then also note that the infimum of f plus g over partition. So in this case we have the reverse. This will be greater than or equals to infimum f of p plus infimum f of p. So with this condition also, and with the definitions of the Riemann sum, so this we have this. Oh, this should be G. And that concludes the proof. So here also you can make this more explicit by taking the lower Riemann sum over partition and then take this find the summation over all the supremum. Take the supremum all over then these conditions out. And that's by that definitions. So let's check question number 4. Number 4. So we are given an example of a bounded function f comma g such that these conditions hold, and then also to give the for the upper Riemann sum also an example that I can think of, and then we can verify it. Example is let f of s equals to sin 2 pi of x, and then g of x equals to sin 2 pi of x. So you know that the infimum of f, so it should be cos. Let's make this cos. So the infimum will always, the infimum of f of x will always be minus 1, and then the infimum of g of x also will always be minus 1, because both of them oscillate between minus 1 and then and 1. Okay, so that means that if you take the lower Riemann sum of these two guys, it's minus 1, then lower Riemann sum of this also equals to minus 1. So if you add them together, and then we reduce this, and we do this, okay. So if you add them together, f of s plus g of x, so you have sin 2 pi of x plus cos 2 pi of x. So the infimum of this guy, if you check the graph, for g of 0, 1 of this guy is equals to minus 2 r, and then we check the upper Riemann sum. Okay, the infimum. Let's go with the infimum first. So if you add up these guys, then you have this guy with this guy here, we have minus 2. So that minus 2 is less than minus 2, and that implies that the addition of these two guys is less than this guy, which satisfies this first condition. Then the upper Riemann sum also, the upper Riemann sum, on this side. So the upper Riemann sum of f, that will be positive 1, and then for G also that will be positive 1. Then the upper Riemann sum of these two guys, that will be positive 2. So let's also take the addition. You see that the 2, so if you take the summation of those two guys, so you see that our root 2 is also less than 2. Okay, and that conclude that. So you can carefully check that. So lastly, let's check the last exercise, then we are done for this section 1p. Then our next video we go straight to measure. So we have given an example of a sequence of a continuous real value functions on 0,1 that is continuous, such that the f of x, the limit exists, and then for each x belongs to 0,1, both integral 0 to 1 of f is not equals to the limit of k tends to infinity of integral 0 to 1 f of k. Right. So an example I can think of now is just a function like this, k of x for 0 less than or equals to x less than or equals to 1 over k, and then k equals to 2 over k minus x for 1 over k less than or equals to x less than or equals to 2 over k, and then for 0 for 2 over k less than x less than or equals to 1 over k. So this is just like a triangle functions. So the pointwise limit as k tends to infinity is not our f of x. So as k tends to infinity, this side shrinks to 0, this shrinks to 0, 0. So this shrinks to 0, 1, so everything will be equals to 0. So that means that our pointwise limit function for all x equals to 0 equals to this. So you can verify the condition. All this is actually continuous function. Okay, so you can verify that, and then you can also verify the integral. We check the integral of fk of x 0 to 1, so we can break this into pieces. Ks 0 to 1 over k plus 1 over k 2 over k k 2k minus x plus integral 2 over k to 1 is 0, and this is equals to 1 for all k. So even though you take the limits, you still get that to be equals to 1, and then you can verify that. Whereas the integral of the limit fk of x that will be equal to integral of 0, because that's our limit function. This equals to 0, and that implies that limit k tends to infinity integral 0 1 fk of x, which is equals to 1, is not equals to integral 0 to 1 f of x, which is equals to 0. So this concludes all the solution of section 1p. So in the next video, we'll be checking properly what is a measure, and then first of all deal with outer measure. Then from there we'll move on to the next theorem in measure integration and analysis. Thank you for watching. Don't forget to subscribe. Hope to see you in the next video.